Good day, welcome to Lecture 4, Graphs of Motion. Here is your learning intention and success criteria. Please complete your KS table. Pause the video while you complete this. Okay, now hopefully while going through that, having a look at this here, we've actually got a few skill type things here. So we need to be able to calculate, we need to be able to interpret, and then finally we need to be able to represent, interpret, and describe. So that one here is kind of a unified thing there, so I've put them all together. So the way I've identified it here is we should be able to know what do gradients and areas for ST, VT, and AT graphs. We'll learn about what those symbols actually mean through this. Finally, how do you turn a graph into a description, and that links up to this one here. And then in terms of skills, well, we need to be able to calculate a gradient. Hopefully in terms of math, that's not really going to be too troublesome, and you need to be able to calculate the area of a graph, and we'll see what we mean by that a little bit later on. Alright, so in our lab, we've been looking at the motion of accelerating objects, something that is speeding up, to be specific. Now, the Excel workbook that I provided for you for this experiment generated graphs of displacement versus time and velocity versus time. Okay. Now, note the language here. So when I say displacement versus time, I do mean that displacement here must be on the y-axis and time must be on the x-axis. So here velocity and then time. Okay, so that's an important thing to keep in mind. Where was I? Now we can also say, and I use this on some of the graphs as displacement as a function of time. Okay, and that word function, this is the important one. This tells us what is depending on what. That's saying that displacement is changing as time changes, or the displacement depends on time here. And that's where this symbol S means. And you'll see this sort of thing pop up a little bit in some of your specialist mathematics or your mathematical methods, where you might be talking as y as a function of x or something like this, and you'll see stuff like this. So this is why we always have displacement on the y and the time on the x when we're doing these sort of functions, because it's going to be linked to our formulas. Now, in the experiment we actually did, the independent variable was actually displacement, and normally we put it on the x-axis because that's the convention we've taught you. But some of the formulas that we're going to be learning over the next couple of lessons, if we graph it this way, where we've actually put our time on the x-axis, it lets us do some useful math techniques. And while it goes against what you've learned for the last 3-4 years of science, that rule that we've been telling you is more of a convention than something that actually has to be followed. You need to represent data in ways that are meaningful. So if you're doing experiments with motion or anything with time, make sure you put time on the x-axis, because there's only, as I've said before to you, there's only one experiment that I do where time doesn't go on the x-axis, and these aren't it. So we need to be able to do a couple of skills. We need to be able to do gradient, and we need to be able to find the area of the graph. So those are the things that we're going after here. So let's have a look at our first graph here. So this is an ST graph. We've got our displacement here, we can see that, and we've got our time here. And so we would call this an ST. Note, we've got S on the x-axis, on the y-axis, and we'll always put S on the y-axis just because it's useful. We've got T down here on the x-axis, and we can see it's a straight line. Now, if we've got a straight line of something, we can work out a gradient. So let's go through and figure out, well, what does the gradient actually mean? Now, the formula for gradient that hopefully you learnt back in grade 8 or grade 9 is that the gradient, we give it the symbol M, apparently has a link to some French word meaning steepness, equals rise over run. Or if we use a bit more, a stronger math language, rise here would be the change in y divided by the change in x. So let's have a look at what our rise is. Here our rise is our displacement. So our rise would equal our change in s. And our run would equal our change in time. So if we make this substitution here, we're going to get that m, our gradient, is going to equal rise over run, which equals delta s divided by delta t. And if we have a look at this, displacement divided by time, or change of displacement divided by change in time, was what we defined as velocity in a video or two ago. So this tells us that the gradient for a displacement time graph is always equal to velocity. Okay, now that's something you're going to need to memorize, because if we get given you data like this, this is a real common question that you have to ask. Okay. If we put t here, if we put time on our x-axis instead, this wouldn't work, and that's why we set it up in this sort of fashion. Okay. So let's have a look at a graph like this. This is a bit more similar to what we would have seen in the lab, and we can see here that it is a curved graph. So that's going to tell us that the gradient's not constant, because the gradient at each of these points will be different. In fact, I will draw a couple on here. Let's just change another color for this for the moment. So here the gradient would be something like this, while here the gradient would be something like this. And we can see here that the steepness of this red line here is a lot shallower than the steepness of this red line here. So that one's a little bit thinner. So let's just make that a bit thicker for you guys. Okay, so we can see here, this is not as steep as this, and so the gradient is always changing, which means if the gradient is always changing, and gradient equals velocity, therefore velocity is changing. Okay, so we can't use the whole line to work out a value for v at any one point. In our previous graph, we actually could. So in the previous one, we could take the whole straight line and work out the velocity at any one point, because it was always going to be the same. But on here, we can't. Okay. And so because it's curving, we know there's an acceleration. We can use these tangent lines that we've drawn and measure that. Okay, so this tangent here, and this is an important thing because we've learnt about this word before, but now we're actually seeing it, equals the instantaneous velocity. So if I wanted to know the velocity at t equals 1 here, I would draw my gradient, so my tangent here, and work out the gradient of this line. Now, I can make the gradient go, so the tangent go as long as I wanted in order to make it easier to figure out, but I still have to take a tangent to the curve and then to get the gradient of that new tangent line. If we knew an equation that sort of plotted this line out, we could certainly work out the do some fancy calculus with it, or if we knew something about the situation, so we actually knew what the acceleration was, we could use some equations we're going to learn coming up in the next video about how to work these out. But without that information, we have to measure a gradient to a straight line and then work that out. Okay, and you just basically have to do it by hand. However, if we wanted the average velocity, we would again need delta s over delta t, which in this case, and I'll draw this in green, this one would be my average. Oh, that was horrible. Let's see if I can draw that a little bit better. Okay, and that would be taking it from here to here. Now we can see that down here, it's going to be, you know, this number here would be higher than this, but up here this is steeper than this is. So we can see that this is not going to be the maximum velocity, it's not going to be the minimum velocity. In fact, it'd be the velocity about here in the middle. So if we've got a curving system like this, if we've got an accelerating system, the average velocity will always be half the maximum velocity. So we can write that down as a good definition as well. In fact, I'll keep that in green. Average V equals half max V. Okay, and that's a useful relationship to understand because you can use it for some things down the track. Okay, and that's everything I wanted to cover on that. So VT graphs, though, have a bit more complexity. We can use the gradient like we just did. Sorry. We can use the gradient like we just did with our ST graphs, but we can also use the area. Okay, and what we mean by the area is the area between the line we plot and the x-axis. Okay, so let's look at our gradient. Again, on a VT graph, we would have, I'll draw this over here, we would have V on this side and T on here. So our gradient equals rise over run. Well, our rise over run in this case is our change in velocity. And our run is still change in time. And this gives us our definition for acceleration. Okay, and we use A for acceleration. And to accelerate means to speed up or to slow down. It's the change in velocity. Anything where the velocity is changing, remember velocity is that vector quantity. It has both magnitude and direction. So if you change direction, it's still an acceleration, such as running around a circle. But here, this is how we define acceleration. That if we have our change in velocity over change in time, we get acceleration. Okay. We're going to go into acceleration a little bit more, but we're just going to put this definition out for you now, so it'll cover more in some other videos. Now, the worst possible graph you could get for a VT graph would be something curving, like this. There are some complex graphs, and I'll show you one of those later on in this video, but this one is horrible to work with because the displacement for this is going to be ridiculous. This tells us that the acceleration is always changing, and so while we can use the same skills we just did to work out the instantaneous acceleration or the average acceleration, there's not much you can actually do with this at your point in your physics career. So this would be sort of a top tier, ultra challenging type question. Okay. But the skills are exactly the same as the real simple displacement time questions, okay? So don't super stress about these sort of things. Let's have a look though, so what sort of graphs you will have to deal with your VT. We've got two graphs here. We've got a sloped one. We saw something like this in our experiment. And we've got a straight one. Okay. Now the area of the graph, and I commonly use the word area under the curve, and that'll make more sense when you do calculus in math methods or specialists. That's interesting for us. So this first graph, it looks similar to what we did in the lab. We see velocity goes up in a straight line. Okay, we can work out the gradient. The gradient tells us the acceleration. But what does the area of it tell us? Now, the size of the area can be found by multiplying the x-axis by the y-axis and considering the shape of the graph. In this case, it's a triangle, so let's draw that on here so that we can see it a bit better. I'm going to change it to green. So this is the area I'm talking about for this graph. So, let's figure out what does this actually mean first. We have here, we're going to use velocity multiplied by time. And we've seen a formula where multiplying velocity by time equals something. Now you might have clued onto this already and go, oh, I can see what this is, but I'll show you a way to figure this out for ourselves because we can do this technique with any graph we do. Okay, and you can use these skills to interpret what they are. So velocity, the units is meters per second, while for time, our units here is seconds. Well, if I have meters per second, meters divided by second, and I multiply it by seconds, we can see the seconds will cancel, and I'm just going to be left with meters. So what is being measured in meters? Well, the only thing we know about meters is either distance or displacement, and since we're dealing with velocity, it must be equal to displacement. And if we look at the equation that we have before, that v equals s divided by t, we can see we could rearrange this. We can multiply this t to the other side and get this relationship here. Okay, so this skill to analyze a graph and go, well, does working out the area give me anything important, is actually a really good skill to have. Now, the thing is, I can't just go, oh yeah, so here it's 5, here it's 15, so 5 times 15, bang, what's that going to be equal to? 75. It won't work like that, okay? We have to consider the shape of the area. So in this case, it's a triangle. So it's going to be equal to 5 times 15 divided by 2. And 5 times 15, as I just said, is 75, and half of 75 would give us 37.5 meters, because remember, we're dealing with displacement. So that tells us from this graph that after 5 seconds, it's gone 37.5 meters. After 4 seconds, it's gone 4 times 12. 4 times 12 is 48, and half of 48 is 24, so it would have gone 24 meters. Okay, and so the area we can see is building up and up, and so the displacement gets bigger and bigger. Over this one here, we can see, oh yeah, 5 seconds, but it's only gone at velocity 3 meters per second. 3 times 5 is equal to 15, and it's a rectangle, so I don't need to do anything fancy with it. We know the formulas for working out the area of a rectangle. Okay, so you have to consider the shape of it for what you're doing. Now, there are some really complicated looking ones where it's basically like a trapezoid, and I'll show you one later on. You don't have to do trapezoid rules if you don't feel comfortable. You can just work out using triangles and rectangles. You just break it up into its less complicated pieces. So the summary for VT graphs is that when we have a gradient for a VT graph, it equals acceleration. I'm going to write Excel for short because I've run out of space there. And if I have the area of a VT graph, it equals the displacement. Okay, so you've got to memorize those. Now, AT graphs, these are not very common. We haven't dealt with acceleration much, so we'll see a little bit more of them as we deal with acceleration more. But if you come to this idea of acceleration, then we find that the area is useful, but the gradient not so much. So let's look at the area. If I have an AT graph, well, the unit for acceleration, you haven't learnt this yet, is meters per second squared. So meters per second squared. And time is seconds. So if we multiply these two together, we're going to cancel one of these seconds out, and we're just going to be left with meters per second. Well, that means then acceleration times time must equal velocity. Okay, so the area of a AT graph equals velocity. If we were to look at the gradient, let's say that I had acceleration and time, and I had something like this. So acceleration was increasing. I mean, we could do it flat as well, but then the gradient would be equal to 0, so it doesn't matter. We know that m equals rise over run, so that would equal acceleration divided by time. That doesn't really help us because we've never seen that before at all, and that doesn't make any sense to us. Let's look at the units. If we go meters per second squared divided by seconds, gives us meters per second cubed. And again, that doesn't help us too much. And if you go do a little bit of research on this, you find that the gradient here, or the rate of change of acceleration, is called the jerk. Gradient of AT equals jerk. And this has at least a little bit of practical consideration. Imagine you're in a car and they slam on the accelerator and you feel yourself get jerked backwards suddenly. That change of acceleration is that jerky feeling. The acceleration you feel afterwards, you just get pushed back steadily into your seat, but it wouldn't change. Then if they slam the brakes on after they've been accelerating, or they stop accelerating and they're just moving forward at a constant speed, you find yourself, you sort of jerk forward a little bit as your body isn't used to the fact that you're trying to do something to work against that feeling of acceleration. So the jerk is that practical sense. Now, this would never pop up in a final exam. It's not part of the syllabus. It might be something you might want to talk about briefly if you do a student experiment on motion and you're looking at rates of change of acceleration at all. But again, that would be just for giggles or for maybe a bit of extension on a student experiment if it pops up. Do not push yourself to try to put something like that in. So we've looked at our three types of graphs. So now let's have a look at a multi-stage graph. And the first thing you might do when you look at this is go, oh god, this is horrible. This looks nasty, but really it's just a few simple things put together, and we need to just break it down step by step. This is a very common type of question for data interpretation, and it is something that I would use on a final exam if I was asking you to do some interpretation of motion. So this is a velocity time graph, so I've got velocity here on the x-axis. I do apologize that font is so small. I'll make it better for next videos. And you can see here that velocity is changing. Okay, it's starting at 0, going up to 2, 4, 6. Here it's not, it's staying at 6. Here it's staying at 0. Here it's staying at -4. And you could be asked to work out average acceleration for just a region. So you might be asked to go, well, what is the average acceleration for that section? And you can go, okay, well, acceleration from a V2 graph is gradient. We can see here the rise is 6, the run is 3, so 6 divided by 3 gives me an acceleration of 2. Okay, and so you can do these things reasonably quickly. So acceleration here, it doesn't want to write on top of it. Accelerate. Oh, that's very weird. Equals 6 divided by 2. Sorry, 6 divided by 3. Would equal 2 meters per second squared. So we could work out the acceleration here, we could work out the acceleration for this bit here, and we could say, alright, well, it's gone down by 6. Acceleration equals -6. Direction is important, so do be aware of that, and it was from 5 to 11, so that's a time of 6, so equals -1 meters per second squared. So, or we could work out the acceleration for a wider region. Maybe they want the acceleration from 0 to 5 here. Okay? And so then if we wanted the average from this section up to here, we could go, well, it went up by 6, but it took 5 seconds, and so that's going to be 1.2 meters per second squared. And we can see that this number is different from this number because the time was longer. So it doesn't matter what they ask you to do, you just got to follow the process along. So you could only ever be asked instantaneous across a region where nothing is changing. So instantaneous here, you could go, well, that's from -4, so from 0 to -4, so that's a -4 drop. Took 2 seconds, so it'd be -2. Same thing here, same thing there. Even on the flat bits, we can just say, oh, it's flat, so acceleration equals 0 because there's no rise and there's no run. Okay? But again, we would just work out each individual section. If we have changing bits, then we would use average. Okay, so that's just important to recognize that average just means change in velocity over a period of time. So we just do that exact thing. The other thing we could be asked to work out here is what is the displacement? Okay. And if we wanted to know, well, what is the displacement from 0 to 11 seconds, you might be tempted to go, oh, but the velocity is 0 from here to here, so there must be nothing. It's not. Okay. Here, what we're saying is that it was going away from its fast, then it stayed its velocity, and then it slowed down, and then it stopped. So there is some displacement here. Now we could work out as a big trapezoid. I don't, care to do trapezoid rules. I can't even remember them half the time. So I would go, okay, well, there's a triangle there, there's a rectangle there, and there's a triangle there. So this triangle here, we know base times height. Base is 3 times height of 6 divided by 2. Okay, 3 to 5, base is 2 times 6. Here we go, 5 to 11, that's a change of 6. Base of 6, height of 6 divided by 2. And then we would just add them all up. Well, 3 times 6, or 6 divided by 2 is 3, so that's going to be 9, plus 12, plus 6 times 3 is 18. 12 and 18 is 30, so that equals 39 meters displaced during that time. But there's this little bit here, and I want to draw your attention to this. So there will be regions sometimes that go below the x-axis. This bit here is saying that I started at 0 meters per second and then went to negative 4 meters per second. That means he went backwards. So this area here is negative displacement, then continued at that velocity for a bit, and then slowed back down to 0. Not that he went forward, it's going up, but that doesn't mean that he's going forward. Okay, he's still going backwards, it's just he's slowing down while he's going backwards. And so if I was to work this section out, I go, well, here it's a triangle, height is negative 4, times went for 2 seconds, divided by 2, so that's going to equal negative 4. This bit here, 14 to 15, is negative 4 times 1 equals negative 4. This section here is again from 15 to 17, so that's going to be negative 4 times 2 divided by 2, again equals negative 4. And if we add all these up together, we get negative 12. You have to keep the negative because it is below the x-axis, so you've got to be real careful with that. And so then if we were to ask, well, what is the total displacement from start to finish, we could go, well, I've got 39 plus negative 12 gives me 27 meters. Okay, so if we look at the story of this, we can go, well, he started going at a constant velocity and he ended up going 9 meters. Then he started constant acceleration, getting faster and faster, and he went 9 meters. Then here he went at the constant velocity, so then he went another 12 meters. Then he slowed down over 5 seconds and went 18 meters during that time. Then he was stopped for a second, then started going backwards. Okay, speeding up, going faster and faster, backwards, and going backwards 4 meters. Kept this velocity for 1 second, going another 4 meters backwards, and then slowed down back to a stop. And during that time, he went another 4 meters backwards. And so in total, he went forward 39 meters and then back 12 meters for a total displacement of 27 meters. That is one of the trickier skills. Okay, so that is the hardest bit, and the chapter reading goes into extensive details with this, with a lot of working out. I want you to read through and complete those entrance slip questions, and we will do more practice on this in class. But this is probably the harder, at this point, this is probably the hardest skill that you've had to do, and so we will do a lot of consolidation of this in class. Okay, so in this video we've learnt the following. We've looked at the meaning of displacement time, ST, and velocity time graphs, so the meaning of gradients for these two types. We've looked at the meaning of areas for VT and AT graphs, and finally there at the end we've learnt how to interpret a graph to describe the motion of an object. Before you come to class, please, you get a little bit more work on this one. I would please complete questions 1 to 3 in chapter 10.4 and questions 1 to 4 in chapter 10.5. Copy your answers into the 1.4 space on eLearn, so there'll be some questions labeled 1 to 3, and then some questions labeled 1 to 4. I'll make sure to make them distinct for you. Okay, so a bit of heavier work for this one, but it is an important skill. Thanks guys, have a good one.